This lecture is going to go over the Earth's atmosphere. We're going to look at the composition, the characteristics, and the change of our atmosphere over time. It all starts with identifying the troposphere. This is where we're going to look at, this is where we live, this is where we spend most of our life. So we're going to look at the thermal structure of our atmosphere. Our lives are lived almost entirely in the troposphere, roughly from 0 to 10 kilometers. The temperature decreases as one increases in elevation. So notice, I start off here, average conditions in our atmosphere, roughly 20 degrees C, and it gets cooler as we rise in elevation. Then we have this region here, which is called the tropopause. It's the region that separates the stratosphere from the troposphere. So the stratosphere is a different set of characteristics. The stratosphere ranges from 10 to 47 kilometers. This is where we find our ozone layer, O3. The ozone layer is a protective shield from ultraviolet light that damages cells on the Earth's surface. Notice that the ozone range is located almost directly in the middle of the stratosphere. Check out the observed warming trend in the ozone layer. So notice, in our troposphere, temperatures cool as you rise in elevation. Then we get this kind of relatively consistent temperature. There's very little change. And then from the ozone and above, we get a steeper slope. It's simply warming faster. You might say, well, why is it warming above or within the stratosphere? Well, this is the direct result of ultraviolet light, the energy being absorbed and re-radiated upward into the air above the ozone layer. As a result, the temperature above the ozone layer actually increases. It warms up. So the stratosphere actually is the opposite in terms of the thermal conditions. The troposphere cools as you rise in elevation. The stratosphere actually warms up. So what is our atmosphere made of? Well, our Earth's atmosphere is dominated by inert or non-reactive nitrogen. Roughly 78% of our atmosphere is nitrogen gas due to its triple bond. It's a very strong bond. It doesn't want to be broken. However, the second most common substance is oxygen. It's roughly 21%. And then there's small traces of argon, it's about 0.9%. And the rest is a scattering of gases ranging from carbon dioxide, neon, helium, methane, krypton, and hydrogen. So we can break this down. So this pie graph here, we can look at nitrogen, 78%, oxygen, roughly 21%, argon, and then all the other trace gases. And so we can look at them concentrations of parts per million. We can take a look at them percent by volume. If we look at carbon dioxide, this is going to be a hot button topic that we'll be looking at in this unit. Carbon dioxide, even though it's only 0.038%, it's still significant. We're going to look at the changing carbon dioxide content. We're going to talk about what the consequences of that are as we move on. So I got to introduce geologic time, because if we're going to look at the history of the Earth, we need to make sure we understand what's going on here. So when we talk about eons, eons are the big chunks of time. They're the largest segments of time. We've got the Precambrian, which is roughly 88% of all time on Earth, and then we have the Phanerozoic. Phanerozoic well, there's only two named eons in this case, in the Phanerozoic. So big chunks of time. We break down the eons into eras. Eras we can talk Paleozoic, Mesozoic, and Cenozoic. So we break down the Phanerozoic eon into Paleozoic, Meso, and Cenozoic eras. We can break down the eras further into periods. Periods are the breakdown as to what was going on Earth, right? Simply during the eras based on fossil records. And then lastly, so here are the periods. And then lastly, epochs. Epochs are the breakdowns of periods, more recent time frames. So we'll come back to the geologic time part. So let's just look at this graph here. So Earth's atmosphere has not been constant in its chemistry and composition. It has changed over the course of geologic time. It is apparent, right, according to the concept of Gaia, that photosynthetic organisms have modified the atmosphere to its current composition of 21%. These very organisms have helped regulate the 21% oxygenated level. So let's look at this picture a little further. Let's go back in time. Roughly 4.5 billion years ago, not a whole lot going on. It wasn't a whole lot of life going on. It's kind of the early phases of the Earth's development and formation. However, about 3.8 billion years ago, we started finding the first fossils of living cells. The fossils were found in different types of rocks. Well, let's just keep on moving on here and continue finding fossils. And finally we find photosynthetic fossils. Fossils that had something that were, let's just say, processing sunlight in the process that we're going to call photosynthesis. So now we start putting together this timeline. And then it took a couple billion years a little bit later, right? And then plants formed. And then plants forming, plants start taking over land, and then all of a sudden we start taking off this increase in oxygen. So when we look at this graph here, we go from next to very little to zero oxygen in the atmosphere to a 21% which is where we have it today and right now. So why did that occur? Why do we have oxygen all of a sudden? Well, it's simply a few billion years of burping and farting of microbes. Most photosynthetic organisms are oceanic phytoplankton. They're symbiotic algae and bacteria, right? They work together. These are the organisms responsible for oxygenating our atmosphere. The result of photosynthesis is oxygen, and the gas microbes release. Over a few billion years, it's accumulated to today's 21% composition. Here's a bluish green streak here that we see from just a large number of phytoplankton. So here's your phytoplankton. That over time, the phytoplankton in our oceans actually simply release the oxygen. They're photosynthesizing sunlight, carbon dioxide, and water. We'll look at that here in just a moment. These make the basis of the food chain, so they're very important for both the oxygen and the food that they provide. So let's go back and reference what we saw a little bit ago with the geologic timescale. And this will take a little while for you to get some mastery on, but here goes. If we look here at the evolution, which I call the oxygen revolution, every major mass extinction has coincided with a sharp fall in oxygen levels, whereas land colonization coincided with rising sea levels. So where we find dips and blurbs on here, we can actually describe very, very obvious changes that took place on Earth's history. The Earth's atmosphere has a topsy-turvy history of oxygenated atmosphere. It has fluctuated, and such fluctuations have coincided with mass extinctions on Earth. Photosynthesis is the chemical reaction between sunlight, CO2 synthesized in the sugars, and oxygen gas. That as I look at this graph here, and I see that 21% oxygen is today's composition, historically it's been lower and it's been higher. And there are times in which we would find these peaks and these valleys, and there's a reason for them. And we simply just define them as those as mass extinctions. Something happened. Mass extinctions coincide with changes and alterations in our atmospheric composition. So what is a mass extinction? Well, mass extinction is a relatively sudden global decrease in the diversity of life forms. Mass extinctions have occurred periodically throughout geologic time, and there's 5 big ones. 440 million years ago, at the end of the Ordovician, 300 million years ago, at the end of the Devonian, 252 million years ago, 200 million years ago, and 65 million years ago, right? If I'm looking at the geologic timescale, where this is older and this is younger, and then here we are today. So these changes that have taken place, if I go back and I look at my geologic time frame here, you would see that the Precambrian Eon is most of geologic time, and therefore our Phanerozoic Eon is actually much more recent, a smaller segment. So what was taking place on Earth during geologic time? Well, really we know this by studying fossils. Some of the earliest fossils ever recorded date back to about 3.6 to 3.8 billion years ago. And then we start finding the earliest shelled organisms. We're talking about much more recently, just over roughly a billion years ago to just under a billion years ago. And then we have our first fish, we have our first land plants, we have our first amphibians, we have our first reptiles, we have our first mammals, we have Pangea beginning to break up, we have Rocky Mountains forming, we have dinosaurs going extinct, formation of Himalayan mountains, we have the Ice Age. Notice recently, we have the Ice Age, the Great Ice Age beginning and ending until we get to our recent or modern time frame. So geologic time is dated with these events that took place on Earth. That's very well documented in rock. So we need to study rock to understand what's taking place on Earth, not only what was taking place on a global scale, but what was taking place in terms of the atmosphere as well. So let's look at what's happening with our atmosphere. So we have to identify what the greenhouse effect is. This is describing how sunlight is let into our atmosphere and gases trap and hold on to enough heat to allow for water to be found in a solid, liquid, and gaseous state on our surface. Right? Liquid water, very good. Liquid water is a critical component that allowed for life to evolve on Earth. Water, a liquid medium, provides a perfect medium for complex chemical reactions to take place in singular and multicellular organisms. When looking for life in the cosmos, look for water, and then look for life. So the idea of what's taking place in the greenhouse effect, we have to break this down a little further. We have to look at the modes or the mechanism of heat transfer. There's 3 primaries. We have conduction, convection, and radiation. So if I look at this, somebody boiling water, I can actually study all 3 at the same time. So let's talk conduction. Conduction is the transfer of energy through matter by molecular activity, direct contact. Energy is transferred through collisions from one molecule to another, with heat flowing from higher temperature to lower temperature. So here's my heat source. It's going to be transferred from the bottom here. Once I start heating the water at the bottom of this pan, convection takes over, the transfer of heat by mass movement of circulation within a substance. Convection takes place in fluids, liquids like oceans and gases like air, where the atoms and molecules are free to move about. Hot material rises and cooler material sinks. And lastly, radiation. Radiation, or energy, travels out in all directions from its source. Unlike conduction and convection, which need a medium to travel through, radiant energy readily travels through the vacuum of space. All three of these phases or mechanisms of heat transfer take place simultaneously within our atmosphere. So now we have to start looking at paying attention to the sun and what is it doing in our atmosphere. So I call it the fate of incoming solar radiation. Some of the light is reflected, some of it is scattered, some of it is absorbed. Reflection is the process where light bounces back from an object at the same angle in which it encounters a surface with the same intensity. Scattering produces a larger number of weaker rays that travel in different directions. Our sky is blue as a result of scattering. Blue is preferentially scattered the most and absorbed by the atmosphere last, so we view it as blue. A term I haven't written on here that you should pay attention to is called absorption. Because 50% of all direct sunlight that's coming into our atmosphere is absorbed by land and water. So absorption is another key term. I just didn't happen to have space to write it over here. So it's absorbed. It simply increases the thermal conditions of that material that it reaches. So back to this original slide here, if I look at just the greenhouse effect, the greenhouse effect is a very good process. We need it. It's not, this isn't to say the greenhouse effect is a bad thing. The question is the greenhouse effect naturally distributing the heat, or are humans changing the atmosphere to a point by burning of fossil fuels, where we're releasing carbon dioxide and methane and other greenhouse gases into the atmosphere that are trapping, that are leading to an imbalance of the heat that is supposed to be escaping? Now, that's for us to determine, for us to understand. But it all comes down to what is happening within the atmosphere. We talk about incoming light coming in, some of it reflects, some of it's absorbed, some of it is scattered. But the net effect is that our planet is warming up. That is for us to determine. Is it a good thing? Is it a bad thing?